All right, so here we go. Let's take a look now. One of the things that I mean, I just had a conversation with the guys who developed this, and we're working on some things like the Blackboard interface. For me, it was going to be easier, but I mean, they're still starting out. They're still trying, but I think one of the things is they want all this stuff to be nice and easy to do. Okay. So I got to get used to seeing all of this stuff. This is like our keypad, so that's fine for me. Now, this problem this problem number one, of course, I start you off with kind of a hard one. All right, so this is what my problem looks like. So it says an aircraft carrier uses a device called a catapult. I've got a young man who was in my youth group 20 years ago or more, who's now he's the same rank as I am now, which cracks me up. He's a commander, or lieutenant commander in the Navy, soon to be a commander because he's a Squadron XO of F-18s, not F-18s. Yes, he's an F-18 pilot. I thought for a second I was saying the Top Gun F-14. No, he's an F-18 pilot. And these are kind of real numbers. All right. So here we go. And I'm not going to mess around with this too much. Now look what we have here. What do we want to find? What is the numerical value of the ratio of the launch force? Oh, that's part C. Let's look at part A. Why don't we start with part A? Okay, select the correct symbolic expression for the magnitude of the average net force, the launch force, acting on the jet during its launch. Say, what? Okay, but here's my numbers. So I'm just going to write them down now, and I'm not going to mess with it too much. Now we need an acceleration here, don't we? So I'm going to try and help you find this, because what I want to do is I want to find what the launch force is. And I'll be honest with you, I don't know which one it is in this mess. Okay. Now this one actually gives, now if we look at the units though, this one actually gives me v squared over a distance. This would be meters squared per second squared divided by meters. Now that does give me a meters per second squared times a kilogram. So that's a candidate. This is not a candidate. This is not a candidate, because I need kilograms meters per second squared. That's what I finally figured out what they're trying to get us to do. This one's a candidate. This one is not a candidate because there's no mass. This one's not a candidate so it's between this one and this one. Okay. Well, let's just figure it out. Let's just figure it out, because let me show you. Because here's what we're doing. So here's problem 1. Here's homework number 5. Problem 1. All right. I've got a mass. I've got a huge massive airplane. Okay. I've got a velocity, final velocity that it's going to be going. Okay. These are all givens. I've got an initial velocity, which is 0. Okay. And I've got a distance that it traveled, which was 71 meters in this case. All right. Now I know this. I know that the launch force is going to equal the mass of that airplane times the acceleration. So that's what they're trying to get you to see. Mass and an acceleration is equal to meters per second squared. And the mass is equal to kilograms. So I need a kilogram, meters per second squared. Now this is what I was talking about earlier. Now look what happens. If I take an acceleration divided by a distance, I'm going to get meters. If I get v squared divided by a distance, I'm going to get meters squared per second squared divided by meters. So that's how that works when I take v squared divided by a d squared. But I don't know if it's 2 times or whatever. I think it's 2, because look, do you remember this formula? I need to find the acceleration. They gave me everything, but I don't know what my acceleration is. Do you remember this guy? V final squared is equal to v naught squared plus 2 times a times we're going to just say D. We're going to say D is equal to X final minus X initial. Looky there. This goes to 0. So I got V final squared is equal to 2A times D. So V final squared, or V squared, divided by 2D is equal to my acceleration. So therefore, my launching force should be kilograms, should be meters, V squared over 2D. Was that a choice and I missed it? MV squared over 2D. Where's MV squared? Oh, there it is. Yeah, I was saying it's either this one or this one. And I thought it might be this one. Submit. Yeah, you better submit. And I think I got it right. Hell, I never know. Did I get it right? Correct answer is this. Student. Okay, I did. I got to get used to reading that sucker. All right, so now let's take a look at this. Calculate it for the magnet. Okay, well, we've got everything. We've got everything we need because we found the right expression, because we've got this, we've got this, we've got that. So we don't need to do that. And what is this one? Find the ratio. Okay, so part 3, where we're going to find what is the ratio of the launch force to the aircraft's weight. Now what they mean is when they tell you ratio like that, we're going to take FL divided by mg. Okay. And I hope it's greater than 1. Otherwise, this thing's not launching anywhere. That outstanding young man I know is going to wind up in the ocean if this doesn't work. Okay. But I think it will. So what they mean when they say the ratio, here's what they're asking. And I'm going to let this run. The ratio of FL over mg, because mg is weight, mass times gravity here on Earth. This is the weight. Okay. All right. So let's look at the next problem. I think it's really straightforward. So let's look at problem 2. What did I say? 1, 2, and 5. Let me see. Yeah, I said I'd look at 1, 2, and 5. All right. So here's problem number 2. So I just want to make sure. So the mass of the system of the rocket sled in the figure is 2,100 kilograms. Okay. Notice the normal force, we'll talk about the normal force and all that kind of stuff maybe in class on Tuesday. Normal force going up, weight going down. It's not flying up in the air and it's not crashing through the center of the Earth, so those two forces cancel each other out. What do I need to know? The thrust of the rocket is, and the force of friction opposing the most is 650 newtons. Oh, this is a good problem. I like this problem. So the mass of this, okay, is 2,100 kilograms. The friction, the opposing force is 650 newtons. And the thrust of the rocket sled is 2.59 times 10 to the 4th newtons. Oh. So here's how we set this up. This is so important. Okay. This one is sum of the forces in the y direction, in the x, sum of the forces in the x direction is equal to the mass of the rocket times its acceleration, which is equal to the thrust is pushing it. Here's the thrust. Force of the thrust is going this way. Okay. And then the frictional force is opposing that motion. F of K. Sliding frictional force. We'll talk more about actual calculating, finding the frictional force, what it all means. But right now we just know, okay, well, there's an opposing frictional force there. So this is what we have. So the net force acting on things, F of the thrust, which is given, minus the frictional force. Okay? And then we got to find the acceleration. This is a great little problem. I like this problem. Okay? This is equal to m times a. Well, that is equal to the sum of the forces in the x direction, all right? Which is equal to ma. So A is equal to the sum of the forces in the x direction divided by the mass of that little sled. But we had to do the analysis, draw the picture, do the analysis. Let's look at problem 5 real fast. The construction work, oh, we didn't talk about for every action there's equal and opposite reaction. I just said it wrong. For every action, there's a reaction in the same direction but in the opposite way. Okay, now you might be thinking, so of course this is going to be 750. Duh. I mean, we just know that. That gets a great yeah. All right, but here's the big thing. Here's the big idea. The problem is, this is problem 1, 2. The problem is this: we tend to think, well, if I push on something, like here's my little mouse. If I push on this mouse like this, then why is it moving when I push on it? Because it's pushing back with, let's say I push on this with a 5 Newton force. 1 Newton's about the weight or the force of 1 tennis ball is a Newton. That's about a Newton. If you just want to have an idea of what a Newton, the magnitude of a Newton. So anyway, push it like this. So I'm pushing it like that, but it's pushing back with the same force. I'm so massive, that little bitty 5 Newton force, that I don't care. I don't feel it. It's not moving me. It's like when you're walking, you push back on the earth. Does the earth start spinning like you're on a treadmill? No. It goes, your little punk ass, well, your little mass, that's not going to affect me. All right? So, same thing here. It's got a net force of 5 newtons going this way. Yes, it's pushing back with 5 newtons force, but that's not what I'm calculating. I'm calculating the net forces actually. Right now, the net forces are equal to 0. I'm introducing a net force now that's pushing it in the y-axis, we'll say, at 5 newtons. If I knew its mass, we could calculate what its acceleration was. Okay? All right, we're done.